In November 2024, a cargo spacecraft called Tianzhou 8 docked with China's Tiangong space station, carrying something unusual inside. Not equipment, not food, not scientific instruments in the traditional sense. It carried a small box of bricks. But these were not ordinary bricks. They were the first batch of construction material in human history, designed to replace concrete entirely. And the results coming out of laboratories in Wuhan have international researchers asking a very serious questions. Has Chinese science just made one of the most important materials on Earth obsolete? To understand why this matters, you have to start with concrete itself. Concrete is the second most consumed substance on the planet after water. Globally, we produce more than 1 billion metric tons of cement every year. China alone produces over half of that. And here is the problem nobody talks about. Cement production is responsible for approximately 8% of all human carbon dioxide emissions. If the cement industry were a country, it would rank as the fourth largest greenhouse gas emitter in the world, behind only China, the United States, and India. For over a century, engineers have tried to fix this. Many alternatives have been proposed. Most have failed in real-world testing. Carbonatable concrete works for small blocks, but breaks down in large structural beams. Geopolymer concrete is durable, but expensive. Recycled aggregate concrete loses strength after multiple cycles. The fundamental issue is that traditional Portland cement, the binder that gives concrete its strength, requires temperatures around 450 degrees Celsius to produce, and that process releases massive amounts of CO2 regardless of how the heat is generated. That is the problem researchers at Huazhong University of Science and Technology in Wuhan, China, decided to attack from a completely different angle. The breakthrough came from a team led by Professor Ding Lieyun at Huazhong University. His research group, which includes scientist Zhou Cheng, was originally trying to solve a very different problem: how to build a base on the moon without shipping materials from Earth. Transporting just 1 kilogram of cargo to the lunar surface currently costs between $50,000 and $100,000. Building a habitat from Earth-sourced materials is economically impossible. So the team began experimenting with lunar regolith, the loose dust and soil that covers the moon's surface. They used 5 different simulated lunar soil compositions. They tested 3 different sintering processes, a technique that uses high temperatures to fuse particles into solid material. And what they discovered was unexpected. The bricks they created from lunar regolith were not just slightly stronger than concrete. They were measurably and consistently 3 times stronger than standard red brick or concrete. A single 1 square centimeter surface of these bricks can support over 1 metric ton of weight. That is structural performance that no current concrete on Earth can match without significant steel reinforcement. The research was published in peer-reviewed Chinese engineering journals throughout 2024 and 2025. According to the team's data, the lunar bricks survive extreme temperature swings, ranging from 180 degrees Celsius during lunar daytime to minus 190 degrees Celsius at night. They resist cosmic radiation that destroys most organic materials. They maintain structural integrity under vacuum conditions. And critically, the bricks feature an interlocking mortise and tenon design, a traditional Chinese carpentry technique adapted for construction. This means they can be assembled without any mortar, adhesive, or external binding material. Just the bricks themselves, fitting together like a giant 3-dimensional puzzle. Professor Ding's team published these results, and Chinese space authorities immediately recognized the strategic significance. If this material could be made from lunar soil on the moon, it could also be made from terrestrial materials on Earth. And the implications for the global construction industry, which currently generates trillions of dollars in annual revenue and 8% of global emissions, were enormous. Now let's talk about the science. Sintering is not new technology. Engineers have used sintering for centuries to produce ceramic tiles, refractory bricks, and industrial components. What is new is how the Chinese team applied it. Traditional sintering for ceramics requires extremely controlled conditions, specialized kilns, precise atmospheric environments, and careful temperature curves over many hours. The Huazhong team's process is different. Their sintering technique uses temperatures between 1400 and 1500 degrees Celsius, applied in carefully timed bursts. The result is a brick that is denser, more uniform, and significantly stronger than conventional ceramic materials. The interlocking design is equally innovative. Each brick has precisely machined protrusions on one face and matching recesses on another. When two bricks are pressed together, they lock mechanically. This means stress applied to one brick is automatically distributed to its neighbors. Walls built from these bricks behave less like stacked stones and more like single continuous structures. Earthquakes, temperature changes, and dynamic loads are absorbed across the entire wall rather than concentrated at weak points. This is the kind of engineering insight that takes decades to develop. The team had been working on this since at least 2019. By late 2024, they were ready to test their bricks in the harshest environment imaginable. But producing bricks is only half the problem. To build a base on the moon, you need a machine that can manufacture bricks on site, without Earth-supplied energy, without shipped raw materials, and without human supervision. That challenge fell to a parallel research team led by Weiren, chief designer of the Chinese Lunar Exploration Program. Speaking to China Central Television in 2025, Wu announced that his team had developed what he described as the world's first device capable of producing bricks directly from lunar regolith using only solar power. Here is how it works. The device collects sunlight using a large mirror array. The concentrated sunlight is transmitted through fiber optic cables to a focus chamber. Inside that chamber, the lunar soil is heated to temperatures between 400 and 500 degrees Celsius. At that temperature, the regolith melts into a molten state. A 3D printing mechanism then shapes the molten material into bricks of various specifications. The entire process requires no electrical power from Earth, no fuel, no transported chemicals, just sunlight, lunar dust, and a machine that fits inside a standard cargo container. If proven on the moon, the same principles can be applied on Earth using solar concentrators to produce structural bricks with a fraction of the carbon footprint of traditional cement. On November 15, 2024, the Tianzhou 8 cargo spacecraft launched from Wenchang spacecraft launch site. Inside its payload bay was a collection of lunar brick samples produced by the Huazhong University team. The destination was the Tiangong space station, where the bricks would be exposed to actual space conditions for the first time. This is critical for understanding their real-world durability. Laboratory tests on Earth can simulate vacuum, radiation, and temperature swings, but space itself is the only environment that combines all these stresses simultaneously. The bricks will remain mounted on the exterior of Tiangong for approximately 1 year, exposed to direct cosmic radiation, micrometeoroid impacts, and the unfiltered solar spectrum. According to Xinhua News Agency, reporting from late 2024, the first batch of space-tested bricks is expected to return to Earth by the end of 2025 for detailed analysis. If they survive, and current data from the laboratory suggests they will, then China will possess a verified, space-tested construction material that no other country has produced. The strategic implications go beyond science. This is a head start of at least a decade over any competing space program. Let's get more specific about what these bricks can actually do. Compressive strength is the standard measure for construction materials. It tells you how much pressure a material can withstand before it crushes. Standard concrete used in residential buildings has a compressive strength of around 30 to 40 megapascals. High-grade concrete used in skyscrapers can reach 80 to 100 megapascals. The Chinese lunar bricks, in laboratory tests, have demonstrated compressive strengths exceeding 100 megapascals consistently. Some samples have shown over 130 megapascals. To put that in perspective, a single brick the size of a paperback book could theoretically support the weight of 2 small cars stacked on top of each other. The material also displays remarkable thermal stability. Concrete begins to lose strength at temperatures above 300 degrees Celsius. The Chinese bricks remain structurally sound at temperatures above 1.0 degrees Celsius. They also do not crack or shrink during temperature cycles, which is the failure mode that destroys most concrete structures over decades. Engineering Professor Mehdi Khanzadeh at Temple University in Philadelphia, who has been researching alternative concrete since 2021, recently commented that materials with these properties, if validated at scale, could fundamentally change how civilization builds structures. That assessment is shared by researchers at MIT, ETH Zurich, and several major European universities now reviewing the Chinese published data. Now here is what makes this story significant for everyone watching. Regardless of any interest in moon bases, the same engineering principles can be applied here on Earth today, and China has already begun. In February 2025, China National Building Material Group, known as CNBM, opened a new production line at its Henan plant focused on what the company calls low-carbon cement. This is not the lunar brick material directly, but it incorporates many of the same engineering insights. The new CNBM cement uses carbon capture, utilization, and storage technology to reduce CO2 emissions by approximately 30% compared to traditional Portland cement. Meanwhile, Hangzhou Dama Cement Company released a product called ECOCem in mid-2025. This material partially replaces ordinary Portland cement with a combination of fly ash, blast furnace slag, and silica fume, supplementary cementitious materials in industry terms. Studies show ECOCem reduces thermal cracking and resists environmental degradation better than standard concrete. Other Chinese manufacturers are following. Anhui Kong Cement, China Resources Cement, and Shanshui Cement Group have all launched low-carbon product lines. According to a Global Market Insights report published in September 2025, the Chinese low-carbon concrete market is projected to grow from $850 million in 2024 to $2.91 billion by 2034, an annual growth rate of 13.2%. The industry is shifting fast. What does all this mean for the global construction industry? The traditional model, quarrying limestone, heating it to extreme temperatures, mixing it with water and aggregates, pouring it into forms, has dominated for nearly 2 centuries. That model is now being challenged from multiple angles simultaneously. On one side, Chinese researchers are demonstrating that fundamentally new materials, like the Huazhong lunar bricks, can outperform concrete in strength, durability, and longevity. On another side, manufacturers like CNBM are producing low-carbon variants that maintain industrial-scale production while cutting emissions significantly. Together, these developments are putting enormous pressure on Western cement producers, particularly in North America and Europe, who have been slower to adopt alternative materials. Companies like LafargeHolcim, Cemex, and Heidelberg Cement have announced their own low-carbon initiatives, but the scale and pace of Chinese investment is currently unmatched. There is also a research dimension. Northwestern University in the United States announced in March 2025 that researchers Alessandro Rata-Loria and Jeffrey Lopez had developed a carbon-negative building material using seawater, electricity, and CO2. The material can hold over half its weight in trapped carbon dioxide. In December 2025, a separate American team published a paper in the journal Matter describing an enzymatic structural material that absorbs CO2 during production and sets within hours. The race is on, and for the first time in modern industrial history, the leading position in construction materials science may belong to China. Looking forward, the timeline is aggressive. The first space-tested lunar bricks returned from the Tiangong space station in late 2025, exactly as predicted. Research papers analyzing the post-base samples are expected to be published in 2026. Chinese space authorities have confirmed that the Chang'e 8 mission, scheduled for 2028, will carry a prototype of the solar-powered brick-making device to the lunar surface for in-situ testing. By the early 2030s, if the technology performs as expected, China plans to use these bricks to construct the foundational structures of the International Lunar Research Station, a project being coordinated jointly with Russia and other partner nations. On Earth, the timeline is even shorter. CNBM has announced plans to expand its low-carbon cement production capacity to multiple provinces by 2027. Hangzhou Dama Cement is licensing its ECOCem technology to construction projects in Southeast Asia. The Chinese Ministry of Housing and Urban-Rural Development has issued guidelines requiring at least 30% of new public infrastructure projects to use low-carbon construction materials by 2030. This is not a slow transition. This is a coordinated government-backed industrial shift that is being executed faster than most observers expected. Whether the lunar bricks themselves become commercially viable on Earth remains to be seen. The sintering process is energy-intensive, but the underlying research is already accelerating cement industry transformation worldwide. So is concrete really being replaced? Not entirely, not yet. The construction industry is too vast and too entrenched for an overnight revolution. But the foundation for that revolution has now been laid. If this video gave you a clearer picture of what is actually happening in materials science right now, hit subscribe to follow more deep dives into the technologies reshaping our world.